Hi, hi, hi! Today we are gonna be talking about earthquakes. Okay, I'm gonna be very boring, so let's get started. Earth's outer shell is broken into enormous pieces called tectonic plates. These plates slowly move because heat escaping from Earth's interior drives movement within the mantle. Usually, this motion is almost impossible to notice, but sometimes the edges of plates become locked by friction, pressure builds, rock bends, and eventually the stress becomes greater than the strength of the rock. The fault suddenly slips. That is an earthquake, and humans have been experiencing them for thousands of years. The earliest earthquakes. Long before seismometers existed, peoples could only describe earthquakes by what they saw. One of the earliest known written earthquake records come from ancient China. In 1831 BCE, a major earthquake was reportedly recorded in what is now Shandong province. Centuries later, Chinese scholars began systematically documenting earthquakes. In 132 CE, the scientist Zhang Heng created one of the history's earliest known seismoscopes. It couldn't measure an earthquake's magnitude like modern instruments. Instead, it was designed to detect distant ground motion and indicate the direction from which an earthquake had come. This was an incredible idea for its time. People were beginning to realize that earthquakes weren't simply mysterious events. They could be observed, recorded, and studied. But humans still had no understanding of what actually caused them. Pompeii, 62 CE. In 62 CE, a powerful earthquake struck the region around Pompeii and Naples in Roman Italy. Buildings were damaged throughout the area, and this disaster became especially significant because it happened only 17 years before the famous eruption of Mount Vesuvius. The earthquake showed how vulnerable Roman buildings could be to violent ground motion. But there was something scientists now understand that ancient people didn't. Earthquakes don't necessarily come from volcanoes. Most are caused by tectonic forces. As plates move, enormous stress accumulates along fault. When the fault finally slips, the rock on either side can suddenly move by meters. That movement releases stored energy as seismic waves, and those waves are what shake the ground. Lisbon, 1755. One of the most important earthquakes in history struck Lisbon, Portugal in 1755. It happened on November 1st. The earthquake was enormous, and the shaking lasted for several minutes. Buildings collapsed throughout the city, then fires broke out. And because the earthquake occurred offshore, the movement of the seafloor generated a massive tsunami. Ocean water surged through the Portuguese coast. Lisbon was devastated. The disaster killed tens and thousands of people and shocked Europe. But it also changed science. For perhaps the first time on such a large scale, people began seriously questioning the idea that earthquakes were supernatural events. Scientists and philosophers began collecting observations and searching for natural explanations. The earthquake was becoming something that could be investigated scientifically. San Francisco, 1906. More than a century later, the science had advanced dramatically. On April 18, 1906, San Francisco was struck by a massive earthquake. The San Andreas Fault ruptured for hundreds of kilometers. The two sides of the fault had been moving in opposite directions for over geological time. But the sections of the fault had become stuck. When the rocks finally broke free, the stored strain was released. Seismic waves raged outward, the ground shifted violently, buildings collapsed, and fire spread out through the city. The earthquake became one of the most important events in the development of modern science. Scientists began studying faults not as simply as cracks in the ground, but enormous systems of capable of storing and releasing energy. How an earthquake actually works. So what happens during those few seconds? The rupture begins underground at the hypocenter, also called the focus point. The point directly above Earth's surface is called the epicenter. From the hypocenter, energy travels outward as seismic waves. The first ones are called primary waves, also known as P waves. They compress and stretch rock and can travel through both solids and liquids. Next come S waves. They move rock perpendicular to the direction of travel and can pass through solid but not liquids. Finally, there are surface waves, which travel along Earth's surface. These often produce some of the strongest shakings that buildings experience. Scientists detect these waves using seismometers, and by comparing the arrival times of different waves at different stations, they can determine where an earthquake happened. Japan, 1923. On September 1st, 1923, the Great Kanto earthquake struck Japan. Tokyo and Yokohama were hit by a powerful shocking. But the earthquake reveals something crucial about disaster. The shaking itself isn't always the only threat. Fires erupted across the cities, buildings collapsed, the infrastructures failed, and the enormous areas were destroyed. More than 100,000 people died. The disaster pushed Japan toward increasingly sophisticated earthquake engineering. Scientists and engineers learned that surviving earthquake wasn't simply about predicting them. It was also about designing buildings that could move with the shaking instead of collapsing under it. The modern era. Since then, earthquakes have continued to reshape human history. In 1960, Chile experienced the largest earthquake ever recorded by modern instruments. Its magnitude was approximately 9.5. In 2004, a massive earthquake beneath the Indian Ocean generated a devastating tsunami that killed hundreds of thousands of people across countries surrounding the ocean. And in 2011, Japan experienced the magnitude 9.0 of Tohoku earthquake. The earthquake generated a massive tsunami and caused catastrophic destruction along Japan's northeastern coast. These disasters taught scientists something. Earthquakes are not isolated events. One rupture can trigger landslide fires, tsunami, infrastructure failures, and cascading fires. Why we still can't predict them. Today, scientists can map faults, measure tiny movements of the Earth's crust, monitor seismic activity, but estimate the probability of future earthquakes is something we cannot reliably do. We know where many earthquakes are most likely to occur, we know why they happen, and we know how powerful they are, but it's really hard to know when the exact moment an earthquake finally breaks, and it's very difficult to predict.